In this video, we're going to cover section 8.2, which is all about the Pythagorean theorem and its converse. This is a theorem that we've actually been using this year. We started it in chapter 1 with distance formula. We used it last chapter in some of the shapes that had right angles in them, like the kite, the rhombus, the square. And in this chapter, we're fully studying right triangles. And so it makes sense that we're going to kind of formalize the Pythagorean theorem and learn how to use it both the forwards way and the backwards way. So just a reminder of what the Pythagorean theorem is. In any right triangle, you always have three sides, and two of those sides, the two sides that are attached to the 90-degree angle, those are called legs. And then the side that is across from the 90-degree angle is always called the hypotenuse. And so this theorem states that if you take the length of one leg squared and add it to the length of the other leg squared, it will equal the length of the hypotenuse squared. And so, like I said, we use this is the basis of what we calculated in distance formula. We use this to find some side lengths or different lengths inside some quadrilaterals. And so it's kind of funny that we've been using this ever since chapter 1, but we've never actually proved it. And that's a big focus in this class, is that we're always trying to prove whatever it is that we think we know. So this theorem's really famous for having hundreds of different ways to prove it. In fact, there's one example that one of the US presidents supposedly came up with all by himself that involved a trapezoid. Now, we're not going to take a look at that one today, but we are going to prove the Pythagorean theorem. We're going to show that this actually does work no matter what, okay, in any right triangle. So here's what we're going to start off with. Just a random right triangle with legs of A and B, and with a hypotenuse C. Now, I'm going to take that triangle and I'm going to make 4 copies, like 4 total versions of it, and then I'm going to put those together. So you can see here that this is just simply the same 4 right triangles repeated multiple times. This is side length B here, 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 and here. And then this would be side length A in these 4 places. And then, of course, the hypotenuse side length would be C. Now, there's a couple things we can identify about this picture. And that is the fact that the overall big shape is a square. We can see that it's got 4 90-degree angles in its corners. We also see that every side length of this big shape is B plus A, right? Or A plus B. It doesn't matter which order you add them in. So this is a square with side lengths of A plus B. And then we can see the shape on the inside. Now, the shape on the inside is guaranteed to be a rhombus because all 4 side lengths are C. But is it guaranteed to be a square as well? Well, in order to know that, we would have to look at the angles that are given in the original triangle. So we have the angle here. I'll mark the angle between C and A with a single arc mark, and the one between B and C with a double. So if we go over here, we can see that the angle between B and C, like here, would be a double mark. Here would be a single. This one would be a double. That would be a single. This one would be a double. That would be a single, and so on. Now, the real question is, what do we know about these 2 angles, right? Because ultimately, we know that all 3 of these angles added together should make 180 degrees because they all fit together to make one straight line. If we can figure out what the 2 angles added together would be, we could subtract that from 180 to figure out what the missing angle here would be. Well, that's pretty easy to do because we know that this triangle over here should have 180 degrees in it. So if we subtract away the right angle, what that shows us is that this angle plus this angle should equal 90 degrees. So then if we go back over here to our picture, if those 2 angles added together make 90 degrees, and we can subtract that from 180, what it tells us is that this angle here must be a 90-degree angle. And that goes for all 4 places where that angle shows up. And so what we confirm is that the inner shape is also a square with a side length C. Now, how does this lead to us proving that the leg squared plus leg squared equals hypotenuse squared? Well, it comes down to areas, okay? there's actually two different ways to calculate the area of this shape. Now, one way is to do it in parts. Okay, so we basically have 4 right triangles that are all a part of the area here, right? Kind of like this. See, I think it was like that. And then we also have 1 square with side length C all the way around. Now, we know the formulas for area for triangles and for squares, so we can actually calculate out what the area of this whole shape would be in parts, in pieces. So first of all, the formula for a triangle is 1/2 times the base of the triangle. In this case, the base would be A. Yep, just had to make sure I had that right, okay? And then times the height. Since this is a right triangle, the height is B. And then, since there's 4 of these, we'll multiply this by 4. Now, 4 times 1/2 would be 2. So the whole area of the 4 right triangles around the outside would be 2 times A times B. All right. And then for the square, that one's easy. Since every side length is C, we just do C times C, so we get C squared. So the total area would be these two things added together, 2AB plus C squared. Now that's one way to find the area of this whole shape, but there's another way too. Remember that the side length of this square on each side was B plus A or A plus B. And so we know that the area of a square is always whatever the side length is squared or times itself. So we could do this using the square formula. And so the area would be A plus B times itself. Now you might remember from algebra class that when you do A plus B times A plus B, you have to do this thing called FOILing, right? You have to multiply every piece, each of the 2 pieces here, by each of the 2 pieces here. So you have to do A times A, which would give you A squared, and A times B, which would give you an AB. Then you have to do B times A, which would give you another AB, and then B times B, which would give you B squared. All right, now if you add the 2 parts in the middle together, you'll find that the area of this whole entire shape could be given as A squared plus 2AB plus B squared. Now remember, both of these 2 expressions represent the exact same area, the area of this entire shape. So we should be able to set these 2 things equal to each other since they both represent the same thing. So over here, I'm going to do that. Let me change my color really quick. All right, so on the one hand, we know that A squared plus 2AB plus B squared represents the area, but we also know on the other hand that 2AB plus C squared is equal to that area as well. And you might be seeing where I'm going with this, right? You notice that both of these 2 parts of the equation have a 2AB in them, and they're both positive, which means if we subtract 2AB on one side, we can subtract it on the other side, and in both cases, it's going to cancel out. And the result is that A squared plus B squared equals C squared. And just a reminder, C is the hypotenuse, and A and B are the legs. So this proves that Pythagorean theorem will always be true. The leg squared plus the other leg squared will always equal the hypotenuse squared. All right, so now that we can add that as a theorem that we have proven in this class. But of course, we're going to try to use this to solve some problems, right? Now, the simplest types of Pythagorean theorem problems are the problems that you'll see right here. Problems where you are given 2 sides of a triangle, of a right triangle, and all you have to do is solve for the 3rd side. So these questions are solved as simply as just plugging the values into an equation and then solving it, right? So since we have leg squared plus leg squared equals hypotenuse squared, you just have to make sure you put the right numbers in the right place. So what I usually tell students is the very first thing you should think is, which one is the hypotenuse? In this case, the hypotenuse is across from the 90-degree angle, so it's 21. So we're going to put 21 squared here. That means that 15 squared will go here, and then x squared will go here. And this basically comes down to something where you just move everything over to one side except for the x squared. And then in order to get the x squared down to x, you're going to have to square root it. So 15 squared is 225. 21 squared is 441. So we get x squared plus 225 equals 441. Then we're just going to subtract that 225 over to the other side, which gives us x squared equals 216. Now you can square root both sides, which would give you x equals the square root of 216, which if you type into your calculator, you're going to get a decimal answer for. You're going to get approximately 14 point, if you round it off to one decimal place, it'll be 14.7. Now that's an okay answer, and in real life, you know, obviously if this was a building or if this was something you were crafting in real life, you would want to know the exact answer for that square root. However, there is an aspect of this where I'm going to be asking you to do some of these calculations actually without a calculator. Okay, and so I want to walk you through kind of the process of simplifying a square root so that you can get a perfect answer and not have to use your calculator to get an answer. Some of this is a little bit more difficult than others. Some of it requires you to know your multiplication facts really well. But basically what it comes down to is you want to try to break up that 216 into its multiplied parts. Okay, so one way to do that is to make like a factor tree, right? Some of you have probably seen something like this. So you say, okay, what can 216 be divided by? So the first obvious thing is 2, and then you divide it, and that would leave you with 108. And then if you think about what can that be divided by, you can divide that by 2, which would leave you with a 54. You can divide 54 by 2, which leaves you with a 27. You can divide 27 by 3, which leaves you with a 9. And finally, you can divide 9 by 3, which leaves you with a 3. Now, this is the key aspect of simplifying a square root. You probably learned this in Algebra 1, but you can take out perfect squares from a square root. In other words, you can find groups of 2 multiplied parts inside the square root, and you can take things out in groups of 2. So you'll notice, looking at all the numbers that go into making 216, you can see that there are 2 groups of 2. There is a group of 2 2s, and there is a group of 2 3s. You'll also notice that there's a 2 that doesn't have a matching 2 to go with it, and a 3 that doesn't have a matching 3 to go with it. So basically what you do with this is you take out the groups of 2 and you leave behind the ones that don't fit into a group of 2. In other words, let me illustrate it on this side. If you break 216 up into all its parts, this is what we found. So when we grab this pair of 2 and we bring it outside the square root, it becomes just a single 2. And if we grab this pair of 3s and bring it out, it becomes just a single 3. And so on the outside of the square root, we now have a 2 times a 3, which is a 6. And then on the inside of the square root, we have also a 2 and a 3. And so that leaves us with a 6. The best answer to give for this, instead of typing it into the calculator and getting a decimal answer, we just simplify it and we give the answer 6 square root 6. We'll have an example, we'll have some opportunities to see this happen again. All right, now for this one, I'd like you to pause the video and try to solve this by yourself in your notes. But for my purposes, I'm just going to keep going. All right, now there's actually only one thing we're looking for here, and that's side length AB. But we're never going to be able to solve side length AB without first solving for side length BD. So if you put that into Pythagorean theorem, you would get y squared plus 3 squared equals 5 squared. That would be y squared plus 9 equals 25. If you subtract 9 on both sides, you get y squared equals 16, and square rooting both sides tells you that y is equal to 4. Once you have 4, you can then redo Pythagorean theorem again. 7 squared plus 4 squared equals x squared, and then go through the process of solving. We'll continue this in a future video